what's the roots of an equation? We are interested in this problem. Compute x such that f of x is equal to 0. Okay. Okay, so if x was some complicated expression, x square plus 2 sine x minus 3x cube x, and find x such that that whole term is 0, is not an easy problem. It is kind of an involved problem. So how do we do about solving that? Is the question here. Roots of equations are usually helpful in many fields. When in my field where we are trying to, that is robotics, we are trying to solve problems like, for example, if you're looking at a motion where something is going, let's say take a projectile example. If you want to find where a projectile will hit, you do not know what time it will hit the ground, right? Because hitting the ground is solving for, if y is the height, then you need to find when the projectile will go to y equals 0. So that is a root finding problem, when something will happen in future time. So this will require you to basically try various sort of conditions. You'll try to see if it's going to hit at 5 seconds, 4 seconds, and maybe it will hit sometime between 4 and 5, because you observe that at 4 seconds above there, 5 seconds is below there, that is in a computer simulation, and then you can sort of interpolate and get to the point. So this is what this particular chapter will deal with. Now, if you deal with a problem such as this, sometimes you're told to find a solution such that g of x is, I don't know, just putting some value. Find x such that g of x is equal to 20. Okay. Now this is actually also a root finding problem. The way you can cast it as a root finding problem is you write it as gx x minus 20 equals 0, and then treat this as f of x. So now you have reduced it to the same problem, f of x equals 0. Right? You could have something like this: g of x equals x square minus 2x plus 5. Okay, so you need to find when this equation is satisfied, right? Again, this can be boiled down to a root finding problem as follows. You just move this on the other side. Minus 5 equals 0, and then you treat this whole thing as f of x, and then it's solving a root finding problem. Just ensure that whatever you're solving for is always comes down to an expression like f of x equals 0, because the code which you'll be using, either you'll make it, you will write your own code or use some of the functions available in Octave. They all try to write the equation down. They understand that the syntax is always f of x equals 0, not g of x equals 20 or g of x equals some x squared plus 5x minus 2. So we're going to before we actually get into the numerical part of it, let's just think how we might solve this problem if we had not taken this course. So here's a motivating example. Compute x such that f of x equals x squared plus x minus 2 equals 0. Okay, a quadratic equation. You have to find the roots of a quadratic equation. Now, I'm sure you have seen this before. Solving the roots of a quadratic equation, there's a formula which you can use and solve for the roots of the quadratic equation. But if it was more complicated than that, it was x cubed by x raised to 4. That's a much harder problem to solve by hand. So in such cases, one of the tricks which always works, no matter how complicated that expression is to graph this function. So make a plot of f of x as a function of x. And you can do this by graphing calculator, but you could also do this by hand. So if you have, for example, if you put x equals 0 in this, you have 0, 0, minus 2. So it looks like it is, for x equals 0, it's over here. Put x equals 1, so 1 plus 1 minus 2. It actually turns out to be a root. So at x equals 1, it is 0. And then x equals, let's put 2. 2 square, 4 plus 2 is 6. So it's about here. So it's actually something like this. Okay, so it actually would turn back and come this way. So when you make a plot of this function, you realize there are two roots. Okay, so the one root is x equals 1. What's the other root? Don't even know the other root. Is it -2? See, -2, yeah, it's -2. So this is x equals -2. Okay, so there are two roots, -2 and 1. And the graphing approach is nice because it always works. It always gives you the roots. The problem, however, is this. Now, by far, we're going to do only 1 dimensions or maximum 2 dimensions of f of x. So f could be a function of x, or it could be a function of x and y. If you go to more than 3 dimensions, 3, 4 dimensions, it's just hard to make a plot in 4 dimensions. This is where a numerical method, which we're going to talk about in this course, will help versus doing it using a graph, right? Also, the problem with the graphing approach is that it doesn't give you it sometimes give you very accurate values. Like this case, it was easy to find the accurate value because it turns out that it was an integer. Sometimes those values, the roots would be at, I don't know, 1.43567. Just so hard to get that decimal point on a graph. So a numerical method, which we're going to talk about in this course, will actually give you that root. And sometimes it really matters to compute it accurate to 2 decimal places. Okay, so there are, in this course, what we're going to do is, in this part of the course, we will be using certain methods to do root finding. And there are really 3 steps to root finding. 3 steps for root finding. Number 1, initialize a solution. So what this means is that all these numerical methods require you to start somewhere, make a guess what the root might be. Sometimes that root has to be sufficiently close to the actual solution. Sometimes you can just put it anywhere you want and it will work. Okay, we'll see how this pans out when we write code. We'll actually test this code by trying different initial guesses and see what happens. But you always need to initialize the solution. It cannot start from nowhere. The second step is to get a search direction. Okay, so this is where we figure out the next best guess. So let's say you're far away from the actual solution. Your hope is that the next guess will get you closer to the solution, closer to f of x equals 0. So there are methods which help you do that. So that's the next step. And we'll see a couple of methods which do that. Okay, there's 3 methods which do that. And then the last step is termination criterion. Okay, so what will happen is, well, with termination is basically when to stop. So what will happen is that when you do this numerically, f of x will start decreasing. So maybe it's 5, then goes 4, 3, 2, 1. It'll start getting smaller, 0.1, 0.2, 0.3. It may reach 0.00001, so 1e -5. And then maybe that's good enough and you'll stop. There's only so much accurate you can get because one thing is it takes sometimes some of these methods go very slowly when they come very close to the solution. and so it's not worth waiting so much time, so you just terminate. Sometimes you deal with just computer accuracy, only compute to 13 decimal places, right? So when to stop is one criteria. So typically what people do is they say when f of x, the magnitude, is less than some epsilon, we'll stop. And this epsilon is a small value. It's a user chosen value. You could take 10 raised to -2 or 0.01. If you want to be more accurate, you take 1e -5, 1e -6, and so on. Okay, so that's one way you can terminate. Okay. There's another issue which happens when we use this method. Sometimes what happens is, let's say you say 1e -6, but you know that it takes so much, but because of the way the problem is set up, it takes many iterations to get to 1e -6. So the progress is very rapid till you get hit 0.1, but then it might go very slowly. So what you do is you also specify another way to stop. You say, I'm only going to try 1,000 times, like iterating. Once I reach iteration limit of 1,000, I'm just going to quit because I don't want to spend too much time doing this. So what people do here is they say the iterations, the number of times you choose a new guess should, if it is greater than a maximum iterations, which you specify, it could be a big number, it could be 1,000, it could also be a million, depends on how much patience and energy you have to, or how much time you can wait. You just say stop. Okay, so we'll see all this in action when we write a code.